name is Bhavesh Naresh Kumar Pabnani, a third year undergraduate student of the Department of Mechanical Engineering at IIT Kharagpur. I am pleased to present our project for the course Mechanism Sessional. This presentation is a part of Sheet-5 and has been prepared along with Ayush Pravin Sarayakar and Chinthapatla Swetharca Chinmai. The topic of our project is the analysis and synthesis of a windscreen wiper mechanism. Let's proceed. The objective of our project is to synthesize and simulate the windscreen wiper mechanism shown in the tutorial sheet 2 question 6, ensuring no quick return effect. Our simulation also aims to accurately mark the area wiped by the wiper blade. The schematic provided in the problem outlines the original dimensions and configuration of the mechanism, which forms the foundation for our study. However, as part of the design process, we synthesized and adjusted some of these values to meet operational constraint and ensure the mechanism functionality. In the presentation, we will cover the following key aspects of our analysis: velocity and acceleration analysis of the mechanism, graphical representation of velocity and acceleration, and the torque requirement for the motor. Each topic will be addressed step by step to provide a clear understanding of the design and its performance. The windscreen wiper mechanism is a 4-barge linkage system denoted as O2ABO4. In the original problem statement, the dimensions were specified as follows: O2A, the crank, was 30 mm, AB, the coupler, was 200 mm, O4B, the rocker, was 80 mm, and the fixed distance between O2 and O4 was 158.11 mm. After synthesis, the dimensions were adjusted for better functionality while maintaining design integrity. The coupler was synthesized to 100 mm. The fixed link was revised to 150 mm. To ensure the mechanism's feasibility, we applied Grashof's criteria. This criteria states that the sum of the shortest and the longest link must be less than or equal to the sum of the remaining two links. Substituting the synthesized values, that is 30 plus 80, was less than equal to 80 plus 150. Since this condition is satisfied, the mechanism ensures continuous motion, fulfilling the design requirements for uniform and effective wiping motion. Now I would like to hand over to Chinmai.
Everyone, I am Swetharca Chinmai, a third year undergraduate student of Mechanical Engineering Department. Now we will go through the synthesis of initial problem to avoid quick return effect. The quick return effect is a mechanical phenomena where a mechanism moves faster in one direction than in the opposite direction during its cycle. We are doing synthesis here to avoid the quick return effect. Here we can see the initial position of O2 and extreme positions of A and B, that is A1, A2 and B1, B2. O2 must lie on the line joining B1 and B2 to avoid quick return effect. I am considering length of O2, O4 to be 150 mm and O2A and O2B were already defined 30 mm and 80 mm in the question. Now we would get the length of AB to be 100 mm and we can say that this is a crank rocker mechanism. Let us now perform the velocity analysis using Kennedy's theorem IC method. Here omega 2 is input and omega 4 is output. Here we are doing the velocity analysis using IC method. By doing the IC method, we would get the final answer to be omega 4 is equals to L2 sine of theta 2 minus theta 3 by L4 sine of theta 4 minus theta 3 into omega 2. Here L2 sine of theta 2 minus theta 3 by L4 sine of theta 4 minus theta 3 is known as Jacobian. This constraint will be useful in acceleration analysis. Here in acceleration analysis, omega 4 is equals to Jacobian into omega 2. Here we perform the differentiation of omega 4 and omega 2 to get alpha 4 in terms of alpha 2 and omega 2. So final answer that we would get in acceleration analysis is alpha 4 is equals to dou j by dou theta 2 into omega 2 plus dou j by dou theta 4 into omega 4 into omega 2 plus j into alpha 2. This is the acceleration analysis. So The torque requirement of motor neglecting dynamics. So here we are using the concept of conservation of energy, and we are taking the power output is equals to the power input using conservation of energy theorem. Here power output is nothing but tau motor into omega motor, and power input is tau wiper into omega wiper. Upon equating them both, we will get that tau motor is equals to tau wiper into omega wiper by omega motor. This is the torque requirement of motor. Thank you everyone.
Hello everyone, my name is Ayush Sarayakar. I am a third year student from the Department of Mechanical Engineering at IIT Kharagpur. So I'll start with the simulation part of the project. Over here we have the model made in SolidWorks. You can see it move over here. It is moving perfectly like a wiper. So we'll start with how we made this model. First of all, we had to model up all the individual parts to make this assembly. Over here you can see the various parts involved in the assembly. So this is the ground linkage. This over here is the coupler. Similarly, there are various other linkages in this mechanism as seen. So we have assembled all these to finally get a final assembly. The next part is the simulation part for the video. For this, we have used the SolidWorks add-in known as SolidWorks Motion, which opens the motion study for the mechanism. In this section, you can see how the part exactly moves. Over here, you can see the movement of the model. So I'll just open this up. Once we stop the recording, we can see the motor option. Over here, I'll just edit this. Constant speed of 15 rpm as seen. So this basically gives us the motion as seen. Now the next part of the video is the velocity and acceleration plots. Over here you can see the velocity of the wiper with respect to time. I'll just start the video. So this is how the velocity of the wiper changes with time. Over here the red part is the live position in the graph. Next up, you can also see the acceleration analysis of the wiper. So this part shows us the linear acceleration of the plot of the wiper with respect to time. We can also see the live direction of the acceleration and the velocities as well. Over here, the green arrow represents the velocity of the wiper, whereas the red arrow represents the direction of the acceleration of the wiper at any instant.